Hello everyone, welcome to my class on GPAT 2020 Organic Chemistry Question Analysis. In this video, I am going to explain the concepts in organic chemistry, mechanisms involved in organic chemistry, most importantly logical thinking. How do you think when even if you don't know the concepts and mechanisms, you can still answer questions with logical thinking. I'll explain how to think logically and answer the questions. This is my channel. If you like my videos, do subscribe, comment and like the videos. Let's get into this. Now, one of the questions asked in this GPAT 2020 is, which of the following is anti-aromatic? See, we keep listening about aromatic compounds, but there is a concept called as anti-aromaticity. The uniqueness of aromatic compound is they are highly stable because of resonance. The moment you see the resonance, it confers, it gives stability to the compounds. Whereas in case of anti-aromatic, they are highly unstable compounds. So we need to know the differences between aromatic and anti-aromatic. Look at this slide. See, in order to be aromatic, these all are the requirements. The compound should be a cyclic compound. It should have a conjugated double bonds. That means alternate double bonds. Like benzene, you see there is a double bond and then single bond, and then there is a double bond and then single bond. There is a double bond and then single bond. This pattern is called as conjugated double bonds. Now they need to have 4n plus 2 pi electrons. The n is an integer. Think with the case of benzene. N is 1. If it is 1, 4 into 1, 1 plus 2, 6 electrons are there. Now it should have this number of electrons. Now in benzene you have 3 pi bonds are there. Each pi bond is made up of 2 electrons. So into 3 means totally how many electrons are there? 6 electrons are there. It is satisfying this rule. This is what is known as Huckel rule. Now after that the molecule need to be flat. Flat in another word it is known as planar. The sp2 hybridization gives this molecule a planar shape. That is what is called as flat. So in order to be aromatic, all these requirements need to be fulfilled, and it gives a lot of resonance energy, which is nothing but stability. They are unusually stable. Now coming back to anti-aromatic, they are unstable. See, they also have cyclic structure, they have conjugated bonds, but the difference comes here. They have only 4n pi electrons. Look at this one. See how many electrons, how many pi bonds are there? 2 bonds are there. 2 bonds are made up of 2 electrons. So how many electrons are there? 4 electrons. So n is 1. So 4 electrons are there. Again, this molecule is also flat or planar, and this is unstable. Look at this. It is stable only at minus 100 degrees. So that is why they are called as anti-aromatic. Now leaving this, all other things are called as non-aromatic. Now the concept is this. Now look at this molecule. Now this one, cyclic structure is there. Now count the pi electrons. How many bonds are there? 3 pi bonds are there. That means 3 into 2, 6 electrons. Huckel rule, what does it say? 4n plus 2 pi electrons. N is 1, so 6 electrons. It satisfies aromatic compound rule. No problem. Next one. Again see, 2 pi bonds are there, but here electron pair is there. So how many electrons it will become totally? Again 6 electrons. Again it satisfies Huckel rule. Benzene, you know all, this satisfies 6 electrons. What about this one? 2 pi electrons are there. A positive charge means no electrons. That means how many pi electrons are there? Only 4 pi electrons are there. So this becomes anti-aromatic. So what is the option? This option. Among this compound is anti-aromatic. This is a concept based question. Next one. Now propanone and 2-hydroxypropene. Look at this. This is what is propanone. This is propanone. Now 2-hydroxypropene. This is second carbon. Hydroxy group is there. This 3. So this one, these two. What are these two? Now see, this one is a ketone. This is a ketone. Now what is this? This double bond is known as ene, and alcohol is known as ol, ol, ol. So totally this one is called as enol. So this one is an enol, this one is a ketone. Now these keto-enols are a type of isomers. They have similar molecular formula, but there is a difference in this pattern. So this is called as Keto-Enol Tautomerism. Now, so propanone and 2-hydroxypropene are tautomers. Now understand this one, the arrow indicates these ketones are more stable. So though they exist in isomer form, most of the molecule will be in keto form. Remember this, we have another question based on this concept. Now remaining things, see chain isomers, you know butane, CH2, 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 CH3. Butane can be exist in this form or it can be like this. See, both of them are known as chain isomers. There is a difference in chain. This is N-butane, this is isopropyl butane. So there is a difference, I'm sorry, this is isobutane. So there is a difference in this chain arrangement. So they are called as chain isomers. Position isomers, see when there is a substituent is there, if there is a change in its position, imagine this is this one. What is this? This is chloropropane. What is this one? This is 2-chloropropane. So there is a difference in the position of the substituent, hence they are known as positional isomers. Rotamers, rota indicates rotation. At single bond, when single bond is rotated, that will result in a different kind of isomer. Let us see with an example. Imagine you have a compound like this, a butane, 4-member chain is there. These are also carbons. The dots indicates carbons, and the carbon arrangement is like this. Now, if this bond rotates like this, what happens? You get the methyl group is moved like this. Hydrogen will comes here, and this hydrogen comes here, and the remaining thing is same. Let's say only the rotation occurred at that bond. Now look at these two things. See, both of them are same. The difference occurs at rotation of this bond. So because of the rotation, two isomers are coming, then they are known as rotamers. Now anyhow, getting back to the question, so propanone and 2-hydroxypropene are example for tautomers. Next question. Now hydrated proton. See, this is hydra means water. Hydrated proton means one more hydrogen comes here and it becomes H3O+. This is called as hydronium ion. In hydronium ion, hydra means water, onium means a cation. So water with this cationic charge is known as hydronium ion. This is a simple question. Answer is 2. Moving next. Now electron releasing group stabilizes free radicals by. Now understand this one. Free radicals are characterized by unpaired electron. They have got an unpaired electron. When electrons are paired, it gives stability. When electrons are unpaired, they are not stable. So if any group, if it is releasing electrons, so it gets one more electron and it becomes stabilized. So electron releasing group stabilizes free radical. But what is the concept? The question is based on mesomeric and inductive effect. To understand this, let us see about this. Let's say you have hydrochloric acid, HCl is there. Now when you compare these two atoms, chlorine has got more electronegativity, so electrons are drawn towards chloride. It will be like the electrons will be pulled towards chlorine. So because more electrons are near chlorine, it gives a partial negative charge, and hydrogen is losing electrons, so it gets a partial positive charge. This effect is known as inductive effect. Inductive effect is because of electronegativity of atom and electrons are pulled towards it. Now understand one more thing. Let's say you have a carbonyl compound. Now here also oxygen has got more electronegativity. These pi electrons are pulled towards oxygen and it is converted like this. Electrons are completely displaced and it gets a negative charge here and a positive charge here. You can see the difference here. Only the electrons are moving towards it, but here the electrons completely are moving to this oxygen place. So this arrangement, this movement of electrons from pi or n electrons is known as mesomeric effect. Whereas the movement of electrons only with a single bond getting closer to this electronegative atom is called as inductive effect. Now what do you mean by positive and negative? If a group is releasing electrons, what is happening? This carbon has got lost that electrons and hence it is known as positive mesomeric effect. If any group is giving electrons towards a carbon, then it becomes negative mesomeric effect. Now here what is happening? See, this group is releasing electrons. The moment you see releasing electrons, it is related to mesomeric. If it is releasing electrons, it is losing electrons and it gets a kind of positive charge, hence it is known as positive mesomeric effect. This is a common concept. You need to understand what is mesomeric effect, what is inductive effect is. Positive negative is related to electron release. So the answer is this one. Now, going to the next one. Again, this is a concept based question. Which of the following groups stabilizes carbocation in electrophilic aromatic substitution? Now, the topic is about aromatic substitution. Now, the moment you say electrophilic, you need to understand what is an electrophilic is. Phile means like. Electro means negative charge electrons. So, what is liked by this negative charge? A positive charge. So, a positive charge, this one is known as an electrophile. It tries to get near to the electrons, hence it is known as electrophile. Now, in aromatic compounds, usually electrophilic substitution occurs. Because there is a lot of electrons are present on this ring, the electrophile will try to go and attach here. Now, this electrophile do not have electrons and it is taking the ring electrons. The moment ring electrons are taken, the negative charge is moving towards this electrophile. Hence, here there is an occurrence of positive charge is there. Now, so the question is about this one. This carbocation, a positive charge on the carbon is known as carbocation. A carbocation in electrophilic aromatic substitution. During this substitution, a positive charge occurs. How does this group is stabilized? Now, in order to stabilize, electrons need to be released here. Imagine you have a hydroxy group here. It has got n electrons are there. These electrons moved here to stabilize this positive charge. Or imagine you have an amine group is there. It also has got n electrons. These electrons will move here and stabilize this positive charge. So this is what is the question about. So NH2OH, which has got lone pair of electrons, can stabilize this. What about other groups? Look at them. COOH and carbon is attached here. See, oxygen is more electronegative, so electrons will be pulled here. So it cannot donate electrons, rather it will be pulling electrons from here. The same thing with CHO. The same thing with NCH3+. Nitrogen is surrounded with all these metals, but it is forming 4 bonds, so it is deficient of electrons. It cannot donate, rather it will withdraw electrons. The same thing. Carbon is combined with the electronegative nitrogen, so electrons will be withdrawn. So only these groups will stabilize carbocation. The concept is this one. Moving further. Now, the specific reagent used in Skraup synthesis of quinolines. Now you need to understand what you mean by the Skraup synthesis and what happens with that. Now the synthesis starts with glycerol. Now glycerol has got 3 hydroxy groups. Right. Now this glycerol, in presence of H2SO4 or sulfuric acid, it is converted to acrolein. Now this is what is acrolein is. Now this acrolein is now reacted with, this acrolein is now reacted with aniline. So this is aminobenzene is aniline. Now in the acrolein, the electrons are pulled like this, so these electrons move and hence a carbon will get a partial positive charge and nitrogen electrons will be moving here. So the overall result is it forms a ring condensation. The acrolein carbons will condense like this. Now this is not quinoline. Again you need an oxidizing reagent like nitrobenzene. In presence of nitrobenzene, you will get these unsaturated bonds, and this is what is quinoline is. So this is what is Skraup synthesis. What do you need? Glycerol, sulfuric acid, aniline, nitrobenzene. So which one is this? Glycerol, aniline, sulfuric acid and nitrobenzene. So this is a popular synthesis used to synthesize quinolines. Next one. Nitration of quinolines gives a mixture of, see, just now we have seen what is a quinoline is. Now quinoline compound is this. Now nitration comes with a positive charge. So this, which has got a positive charge, is going towards a negative charge. So this is what is called as electrophile. It likes to move towards electrophile. So wherever electron abundance is there, there the attack occurs. In quinoline, the numbering goes like this: 5, 6, 7, 8. Now, in this quinoline, the pi electrons will be moving continuously. That is why we show a circle in benzene. Similarly, the pi electrons will be moving. When you see that pi electron moving canonical structure, the electron abundance will be more at 5th carbon and 8th carbon. So nitration can occur to 8th carbon or to fifth carbon. So what is the option? 5 nitro and 8 nitro quinolines. Moving further. Now, Walden inversion or complete reverse of stereochemistry occurs in one of the following. Now, in order to understand this, you need to know what is Walden inversion. See, the answer is SN2 reactions, but how the reaction occurs is, look at this. The SN2 substitution nucleophilic reaction is a classical reaction of alkyl halides. X, I have given it as halide. Now, what happens is halogens, this is hydrogen. A hydrogen atom is here. The other attachments are like this, and halogen is there. Now, the nature of halogen is it is an electron withdrawing, so it will try to take the electrons and move away. At the same time, a hydroxy with electrons will come and attack here. So, what is the result? When you see the final compound, in the final compound, this is what happens. Because the OH has attacked here, you will get this compound. Look at the stereochemistry. This is completely reversed. A molecule of this kind has formed, converted to this one. So what has happened? The stereochemistry is inverse. This is called inversion. It is explained by a scientist known as Walden. So it is known as Walden inversion. Now why it is called a substitution nucleophilic? 2 means bimolecular. See, 2 molecules are involved in rate of reaction. Rate of reaction means the rate determining step. Now, in this, the alkyl halide is forming, the halogen is going along with electrons. At the same time, the hydroxy group which starts attacking. Both of them are involved in rate determining step. So, 2 molecules are involved, hence it is known as substitution nucleophilic bimolecular. What is happening? This halogen is being substituted with OH group. That's why it is known as substitution. Nucleophile. What do you mean by nucleophile? Till now we have seen electrophile. Now this one, a nucleophile has got electrons. It has got these electrons. So when it has got electrons, it has got a negative charge. It likes to move towards a positive charge. Nucleo means in nucleus you have protons. Nucleophile means which is liking this positive charge. So substitution of OH is occurring, nucleophile attacks this one, and bimolecular, 2 of the molecules are involved in rate of reaction, hence it is known as SN2 reaction. Now SNI, intramolecular substitution reaction, substitution nucleophilic in aromatic compounds. SN1 is involved with only this one. Imagine the same thing. Let's say you have the same compound. If the rate determining step is formed only by forming a carbocation, imagine this one. Let's say it is forming a carbocation. Only in rate determining step, only one molecule is forming carbocation, or this only one molecule determines rate of reaction, then it is known as SN1. The 1 indicates how many molecules are there in rate determining step. In SN1 only 1. In SN2 the OH is required as well as alkyl halide is required. So the answer is SN2 reaction. You will see Walden inversion. Next one. Now, an aldo pentose can be converted into aldo hexose pi. Now see, now look at this question. This is what I explained about logical thinking. Now what is happening? A C5 is converted to C6. What are you doing? You are increasing the chain, right? Now degradation, what do you mean by degradation? Breaking down. You need to increase the chain. You are not breaking down that molecule. So by looking at the name, you can eliminate this one. The same thing, rough degradation. Again, this one also you can remove it. By why? You need to increase the chain length, not breakdown or degradation. Now you are left with only 2 options. Now when you don't know the answers, you can eliminate choices like this. Now you are left with 2 answers. So getting correct for this answer is 50-50%. So, right? Now the answer in fact here is, now the answer here is Kiliani Fischer synthesis. Now Kiliani Fischer synthesis, how it happens is, let's say we take a aldo, this is 3 carbons, 4, and this one is 5th carbon. This is aldo pentose. Now in order to convert this, a cyanide is used. Now what happens? I will draw only the top one. So this carbon is converted to hydroxy group and a cyanide attachment occurs here. So you are attached a new carbon to this aldo pentose. Now after this, by using lead and barium sulfate, the cyanide is converted to aldehyde group. So what has happened essentially, C5 is converted to C6. This is known as Killer-Kishner synthesis. Kiliani Fischer synthesis. Now understand this one. You need to pay attention to this one. With common logic you can eliminate some of the answers. Next one. Now the product of this reaction. Now see, this is known as hydrazine and base. This is a popular reaction known as Wolff-Kishner reaction. Now Wolff-Kishner reaction, the job of Wolff-Kishner reduction is converting carbonyl to alkanes. So the answer is straight away this one. The carbonyl goes and it forms an alkane. Similarly, you have another reaction is there known as Clemenson's reaction. In Clemenson's reactions, the reagents used are zinc amalgam in presence of hydrochloric acid. Now see the significance. One reaction occurs in presence of acid, another reaction occurs in presence of base. So let's say you have a compound which is acid sensitive, you will use this reagent. You don't use acid. If you have a compound which is alkali or base sensitive, you will use this reagent. These two are important reactions. So the answer is this one. Next, the condensation of an active methylene compound with formaldehyde and amine to form beta amino carbonyl compound. Let us see what is happening here. Look at this. So the reaction talks about an amine, primary or secondary. This amine is condensing with aldehyde, formaldehyde. Now what do you mean by active methylene group? Look at this compound. Now the carbon which is adjacent to carbonyl is known as alpha carbon and the hydrogen is known as alpha hydrogens. All of them are alpha hydrogens. The normal nature of alpha hydrogen is it is acidic. It is easier to remove this hydrogen. Now what happens in this reaction is this hydrogen and this oxygen goes away, it loses a water molecule and it forms this molecule. So in this carbonyl you have these carbons are there, a proton is removed and this carbon is attached. It is a carbon-carbon bond forming reaction and this amine attaches here. Now see, what is this compound? The carbonyl compound adjacent carbon is what? This is alpha carbon, this is beta carbon. So what is the compound essentially you have formed? At beta you have amine is there and this is carbonyl. So this is what is beta amino carbonyl compound and this is Mannich reaction. The product which is formed is known as Mannich base. So the question is about Mannich reaction. Moving further. Now which of the following rearrangement involves migration of a group from carbon to electron deficient nitrogen? See, the answer is Beckmann reagent. But let us understand what is happening here. In Beckmann reagent, it starts with oximes. Second. Now in oximes, CH3, CH2. Now see, these are known as oximes. Now oximes in presence of a proton, what happens is the proton comes here and the proton will take up oxygen electrons. So what happens immediately, oxygen will try to take these electrons and nitrogen is losing electrons, so it becomes a partial positive charge. This is what is meant by electron deficient nitrogen. In the question they are talking about this one. Because nitrogen has got electron deficiency, it tried to grab the adjacent alkyl group. So what has happened? Migration of a group from carbon to electron deficient nitrogen. From this carbon, this group is migrated here and finally you will get an amide. What happens is the nitrogen will get this group and you will form an amide. C1H2 is amide. So this is what happens in this rearrangement. But what has happened? A group is migrated from carbon to electron deficient nitrogen. That is what is known as Beckmann reagent. In Baeyer-Williser, a group will migrate to electron deficient oxygen. In Wilgott reagent, a ketone is converted to amide. Now pinacol, pinacolone, look at this. All means OH. One means C double bond O. This is a kind of oxidation reaction. So now the answer is Beckmann rearrangement. You need to understand this concept in order to answer such kind of questions in organic chemistry. Next one. Now look at this. What is the product of the following reaction? What is this compound? Pay attention and look at this one. These kind of compounds are known as, see, there is a carbonyl compound. The adjacent carbon is known as alpha and this one is beta. They are known as alpha beta unsaturated carbonyls. Now, what is the significance of this one? See, among all these carbonyls, the electrons will be pulled by this oxygen. So this could result a molecule like this. Oxygen will be having a partial negative charge, here a partial positive charge, and double bond is there. Now, an incoming nucleophile, this happens in presence of acids. So acid means H+, the H+ will come on this oxygen. A nucleophile with its electrons will come and attach here. Now, when you count the atoms, so this oxygen is first atom, this carbon is second, this one is third, this one is fourth. The functional group atoms we are counting. So what has happened? At first atom, attachment has occurred. At second atom, attachment has occurred. Sorry. At second atom, attachment has occurred. So these are known as 1,2 addition. Now, whereas you can have one more occurrence is also there. So when these electrons are pulled by oxygen, the adjacent electrons can move and try to give electrons to this carbon, and that result in a molecule like this, O-, but here you will get a double bond and here you will get a partial positive charge. Now, if at all a nucleophile comes, it goes and attaches to this one, a proton attaches here. So what has happened when you count these atoms? This is the first atom, this is the first atom, 2, 3, and this is the fourth atom. What has happened? 1,4 addition has occurred. Now look at this molecule. After forming that, what is this? This is alcohol, OL, and this is ene. So what is this? This is enol. I have explained you about Keto-Enol Tautomerism, and this enol will get converted to keto form because that is what is stable 1. Keto form, and this nucleophile will attaches here. So this will be the final product. Now, the combination of this at higher temperatures, the higher temperatures are always favor 1,4 addition. That means the incoming nucleophile will attach to this fourth carbon. So this is the option. So the concept is based on 1,2 addition and 1,4 addition. 1,2 addition is favored with very strong nucleophile like Grignard reagents, whereas 1,4 addition is favored by carbon, the cyanide nucleophile as well as high temperatures. So the option is this one. Yeah, this finishes all organic chemistry concepts. So these are my credentials, my channel credentials. If you like the video, subscribe, do comment. Thank you.